Our second talk is about Chinese text spam detection, and the speaker is Zhuoren Jiang.
Check. Hi everyone, my name is Zhuoren Jiang. I come from CNC University. It's a great pleasure to introduce our research work here. Okay, which is detect camouflaged spam context via StoneSkipping graph and text joint embedding for Chinese character variation representation. Only when I read it, I realize this title is really too long. Anyway, this is a joint work of CNC University, Alibaba Damo Academy, Wuhan University, and Indiana University, Bloomington. As we all know, Chinese organize over tens of thousands of characters by utilizing their morphological information. Different characters may share the similar glyph and the phonetic root. For instance, from the glyph perspective, character luo, which means naked, looks like ke, which means coarse, while from the phonetic viewpoint, luo shares a similar pronunciation with luo, which means musical instrument. The form of variation can also be compounded. For instance, zhang, which means account, and zhang, which means curtain, have the similar structure and pronunciation. Unfortunately, in the context of spam detection, spammers are able to take advantage of these variations to escape from the detection algorithms. In this study, we propose a new problem, Chinese spam variation detection. That means we investigating an effective Chinese character embedding model to assist the classification model to detect the variations of Chinese spam texts, which needs to address the following key challenges. The first challenge is diversity. The variation pattern of Chinese characters can be complex and subtle, which are difficult to generalize and detect. For instance, in the experimental dataset, one Chinese character can have almost 300 variants averagely and more than 2,000 maximally. So the existing keyword-based spam detection approach can hardly address this problem. The second challenge is sparseness, zero-shot, and dynamics. When competing with classification models, spammers are consistently creating new Chinese character combinations for spam texts. The labeling cost can be inevitably high in such dynamic environment, so the data-driven approach will perform poorly for the unseen data. The third challenge is camouflage. With the common combination knowledge of Chinese and the contextual information, humans are able to consume the spam information even when some characters in the content are intentionally mutated into their similar variants. However, the variation-based spam texts are highly camouflaged for machines. So we propose a new solution, StoneSkipping, to enable Chinese variation representation learning via graph and text joint embedding. This model is able to learn the Chinese character variation knowledge and predict the new variations not appearing in the training set by utilizing the sophisticated heterogeneous graph mining methods. This is a framework of our model. For a piece of text, which is a character sequence with a proposed model, each candidate character can visit the character variation graph like a stone bouncing across a water surface and exploring its glyph and phonetic variation information like the ripples caused by the stone hitting the water. So we call this model StoneSkipping. We think that's a very interesting and appropriate metaphor. In the following part, I will introduce this model in details. There are three core modules in this model are Chinese character variation graph to host the variation information, variation family enhanced graph embedding for Chinese character variation knowledge extraction, and the graph knowledge representation learning, and enhanced bidirectional language model for joint representation learning. We first define the Chinese character variation graph, which can be denoted as two parts. C denotes the Chinese character set, and each character is represented as a vertex in the graph. R is a variation relation set, and the edge weight is similarity of two characters given the target relation type. To accurately characterize both phonetic and glyph information of Chinese character, we utilize three different encoding methods. The first method is pinyin. Pinyin system provides phonetic-based information, which is widely used for representing the pronunciation of Chinese characters. In this system, each Chinese character has one syllable, which consists of three components: an initial, a final, and a tone. There are four types of tones in modern standard Mandarin Chinese. And the different tones with same syllable can have different meanings. For instance, the pinyin code of luo is LUO3, and the luo is LUO2. The pinyin-based variation similarity is calculated based on their pinyin syllables with the tones. The second encoding method is stroke. Stroke is a basic glyph pattern for writing Chinese character. All Chinese characters are written in a certain stroke order and can be represented as a stroke code. Here's an example of luo and ke. We calculate the stroke-based variational similarity based on the longest common substring and the longest common subsequence matrices. The third encoding method is zhenma, which is another important means for a glyph character encoding. It encodes character at radical level. For instance, the zhenma code of luo is WTKF, and the ke is SKF. The zhenma-based variational similarity is calculated based on the Jaccard index metric. Let's go back to the framework. Unlike previous work only employ one kind of glyph-based information, we utilize two different glyph-based patterns, stroke and zhenma, to encode the Chinese character from the different internal structural levels. We also apply pinyin to provide the phonetic information. The constructed character variation graph integrates these three kinds of variation relations. While the graph can provide a comprehensive knowledge of Chinese character variations, efforts need to be made to address these two problems. As aforementioned, the variation patterns can be very flexible, and the compounded variation information transfer may exist. Therefore, short-range graph information, for example, the character vertex neighbors may be insufficient for the spam detection. Meanwhile, it is impractical to exhaust all possible variation patterns, right? And the second problem is to oblige user to consume the text content. The spammers cannot make the variation patterns to be too complex or confusing. They usually focus on the most sensitive words in a spam message. Hence, some random infrequent variation patterns can be noisy for this task while polluting the detection outcomes. So we propose a variation family enhanced graph embedding to address this problem. We introduce a set of latent variables which named character variation families. Each family is a distribution of characters which aims to estimate the global frequency variation dependency in graph. And by learning the variation family, the embedding method is able to highlight the useful variations, eliminating the noisy patterns and predicting the unseen variation forms with respect to the task. And this method is a random walk-based graph model. So we employ a hierarchical random walk to generate the optimized walking path for each character. After generating the walking path, this method executes following two processes iteratively. The first process is family assignment. By leveraging both local context and global family distributions, we assign a family for each character vertex in a particular walking path, form a character family pair. This is the assignment probability calculation form, and the distribution learning problem can be a Bayesian inference problem, so we use Gibbs sampling to address this problem. The second process is character family representation co-learning. Given the assigned character family pairs, the proposed method can aim to obtain the representations of character and the latent variation family by mapping them into a low-dimensional space. This is the object function. And the learned representation, the learned graph embedding are able to comprehensively keep the variation information in graph. Finally, the family enhanced character graph embedding can be calculated in this form. The generated embedding can provide variation knowledge from the perspective of the graph. In this study, we use an enhanced bidirectional language model to jointly learn variation, semantic, and contextual representation of Chinese character. We propose a combination gate function, which is utilized for combining the variation and the semantic representations. Specifically, there's P, which is preference weights for controlling the contribution from variation information or the textual information. With a combination representation as input, we chain a bidirectional language model for capturing the sequential information. There could be multiple layers, right? So the output embedding is learned from an aggregation function, which aim to aggregate the intermediate layer representations of the bidirectional language model and the input layer. So the outcome can be calculated in this way, and the similar aggregation operation has been applied in ELMO. We validate our algorithm in two real-world SPAM datasets. One is SMS, one is review. And in the constructed variation graph, there are totally more than 25,000 Chinese characters and more than 7 million variation relations. We validate the proposed model in Chinese text spam detection task. In order to simulate the real business scenario, we made a very challenging restriction. That means the character variations were only included in testing set, and all samples in the training set were using the original characters. We use a single layer of CNN classification for the spam detection task. We choose 13 strong baseline algorithms with a comparison group from text or graph viewpoints to comprehensively evaluate the performance of the proposed method. The result is pretty good. The StoneSkipping model outperformed the baseline models and the comparison models for all evaluation metrics on both datasets, which indicate the proposed model can effectively address the problem. For the case study of character similarity, as shown in the table, both general textual embedding and the Chinese embedding baselines are all semantically similar or context related. Unsurprisingly, for the graph embedding, the the similar characters are all glyph or phonetic similar characters. The proposed StoneSkipping model can achieve a comprehensive coverage from variation, semantic, and context viewpoints. This explains why this model can perform well to address the problem. This figure depicts two typical examples in the experimental data sets. We can find that the proposed StoneSkipping model is able to detect both two kinds of spam text effectively. Okay, that brings me to the end of my presentation. We propose an Chinese spam variation detection task to address the real world problem. We propose joint embedding model to learn the variation, semantic, and contextual representations of Chinese characters. And a Chinese character variation graph is constructed for capsulating the glyph and phonetic relations among Chinese characters. We use extensive experiments on both data sets to demonstrate the effectiveness of the proposed method for Chinese spam detection. Okay, thank you.
Questions? So did you use simple baselines to calculate similarity? Like, because you can check up a dictionary for spelling, for example. So you don't have to use the graph to learn this kind of similarity?
Yes, actually, yes, that's a very good question. You can use a very simple method to measure the similarity between the characters, but the graph is a better way to for the complex or the compounded variation combinations. So we think the graph has a great potential for to find the unseen or the new variation combinations for the spam detection task.
One related question is, normally if your character is camouflaged, you can guess possible words out of its similar characters.
Yes.
But did you integrate word information into the model, or is the model, like the correct sequence, somehow pre-trained to ensure that you have knowledge about the possible correct words, like on top of the characters?
Can you repeat your question?
Yes.
Not quite catch.
So, to my understanding, you used a graph to encode like different possibilities of a character.
Yes.
But in the end, in order to resolve ambiguities, you probably want to introduce word information. You can do that either by introducing words, or you can pre-train the sequence models. Did you consider any of these choices?
Yes, that's a very good question. Actually, in our task, the traditional pre-trained model cannot address this problem because the spammers try to create new unseen combinations or the text. So the pre-trained models cannot cover this kind of knowledge. But the graph can provide this kind of knowledge because in the graph, there's only the similarity between the characters. It's not about the semantics or the sequential informations. We use bidirectional language model to character the semantic and the contextual informations. So I think in this specific task, the pre-trained model maybe not can achieve a very good performance.
Okay. All right, let's thank the speaker again.
Thank you.